And please interrupt me if you have any questions. I'm very flexible. So it's a common problem in physics to start with the UV and to go to the IR. And I will be using this color coding that this purple is the UV and this shade of red is the IR. And I'll try to be consistent with this color coding. And it's a common problem in physics to find the long distance behavior of a given short distance theory. And this appears both in particle physics and in condensed matter physics. And one of the main tools that we use is to constrain the answer by matching the global symmetries and their Hooft anomalies. These ideas have been dominant in our field for many decades now, say about half a century or so. And we will continue exploring it. And surprisingly, there are always new things to find out. So what's the symmetry group? Short distances, we have some symmetry group. It's curly G UV. And for the purpose of part of this symmetry, for part of this talk, the global symmetry is a set of transformations that commute with the Hamiltonian. And it's a unitary transformation set commute with the Hamiltonian. We will later generalize that a little bit. And it has a subgroup, ordinary G, that does not act on the coordinates, and we refer to it as the internal symmetry group. So, for example, there could be a U1 symmetry, or there could be a Z2. Now, the larger symmetry group, curly G, can also act on the coordinates, and the way it acts on the coordinate depends on whether we're in the continuum or in the lattice, and depending what kind of lattice we have, the symmetry group would be different. And in general, the internal symmetry is a subgroup of curly G, and the space symmetry is the quotient of this one by that one, rather than being a subgroup. Now, when we go to the IR, it's typically the case that we find a continuum quantum field theory. And again, we have the same story. We have some symmetry group, GIR, and it has an internal symmetry subgroup, GIR. So that might look like a mouthful for saying something that everybody already knows, but soon it will be a little bit different. Now, often the UV symmetry, the internal symmetry, so let's not just focus on the internal symmetry, in the UV and in the IR, usually they are not the same. However, every symmetry transformation, every internal symmetry in the UV is a good operator. It commutes with the Hamiltonian, and therefore it is a symmetry in the IR. And therefore, we have a homomorphism from the UV internal symmetry to the IR internal symmetry. Every element here corresponds to an element here. But this homomorphism is non-trivial in the sense that some UV transformations might act trivially in the IR. So that means that this map has a kernel. For example, imagine we have a system that has a global symmetry U1, which acts only on some massive field, some massive scalar field. At low energies, we don't see the scalar field, and therefore in the low energy theory, that UV symmetry does not act at all. However, more interesting for us is that there might be new symmetries in the IR that do not originate from the UV. And they usually come under the name emergent symmetries or accidental symmetries. In condensed matter physics, they use the word emergent. In high energy physics, they use the word accidental. They mean the same thing. Personally, I think the word accidental is more appropriate for reasons that will soon be clear. They arise when we go to the IR, we try to write a Lagrangian or an action or a Hamiltonian, and we impose only the symmetries that we know for sure are there, namely GUV. But then we realize that we cannot find any relevant operators that violate a larger symmetry. So imposing the condition of writing only relevant operators or marginally irrelevant operators, we find a larger symmetry than what we originally postulated. A typical example is B minus L in the standard model of particle physics. However, that symmetry is not exact, and there are irrelevant operators that violate this new symmetry. So there could be new symmetries in the IR, but they are always approximate, or they are approximate symmetries. And if we talk about B minus L in the standard model, indeed people look for proton decay or neutrino masses, which correspond to high dimension operators that violate B minus L. Now, there is a new phenomenon that can happen, which will be the subject of this talk. There can also be new symmetries in the IR that originate or emanate from the UV space symmetries, typically from UV translation. These are symmetries that are not internal symmetries in the UV, They are in the IR, but unlike the emergent symmetries that I mentioned earlier, there can be relevant operators violating these symmetries. But these operators are not present in the low energy action. So this goes against the rule that I specified earlier, that we get a new symmetry only when it so happens that all the relevant operators in the IR respect the larger symmetry. That's not the case here. There can be relevant operators that violate the symmetry, but they are not present in the Lagrangian. Furthermore, the low energy theory does not even include irrelevant operators that violate these symmetries. So if we perform experiments at low energy, we only limit ourselves to low momentum, low energies, finite number of operators, etc., we might conclude that that symmetry is exact, even though it's not present in the UV. So unlike the emergent symmetries, the emanant symmetries and symmetries that do not exist in the UV, they are not part of GUV, they are in GIR, and they are exact. Phrased that way, it sounds completely impossible. How can we get an exact symmetry out of nothing? But by the time this talk is over, you will say, well, we knew it all along. So it's one of these situations where on one hand, it looks crazy, and on the other hand, it's well known. And as we will also discuss, there could be a Hooft anomaly matching for these symmetries, even though they are not internal symmetries in the UV. There are lots of examples of that. I refer to them as old wine in a new bottle because every one of these examples had been studied earlier in a lot of detail. I will just phrase that in a slightly different language. I'll present a few examples in the talk, depending on how much time I have. The examples I will go through the Majorana chain in 1+1 dimensions, the 1+1 dimensional lattice Ising model, and then I will discuss a global U1 system with a global U1 symmetry with a chemical potential. So these two examples are on the lattice. This example is in the continuum. And if I have time, I will also make some comments about the Heisenberg chain, and I emphasize that there are many other examples. So going to the talk itself, finally the talk starts after this long introduction. The first example we study is very elementary. We have a lattice with L sites, with real periodic fermions. So chi L sits on the sites, and they are real. And we have periodic boundary conditions, namely we use indices that are integers, but we identify chi's that differ by big L. And these chi's satisfy Clifford algebra commutation relations. So by doing that, I specify the degrees of freedom in the Hilbert space. And we impose invariance under two symmetries, lattice translations that maps chi L to chi L plus 1, and fermion parity that just flips the sign of chi L. A typical Hamiltonian to keep in mind is this one. I put the index, the subscript plus here for reasons that will soon be clear. These are just nearest neighbor interactions. And you can check that it's kind of trivial that these two symmetries are preserved. And this system is actually exactly solvable. I will soon do that. This is an elementary exercise in quantum field theory 101. This is one of the simplest systems that we study. But we will study also more. So this is a typical example to keep in mind, but we will have in mind more complicated things. We can add four Fermi interactions next to nearest neighbors, but we will impose these two symmetries. The reason for the subscript plus here is that we will in parallel also study H minus, which is the same system, but with a fermion parity defect, which means that we take one link in this lattice and we just flip the sign here to be minus. Equivalently, we can say that we keep the same Hamiltonian as is, but we make the boundary conditions anti-periodic, which means that we put a minus sign here. These are two different presentations of the same system. Using high energy terminology, we could say this is like Ramon and this is like Neves-Schwarz. And soon the connection to the continuum will be a lot clearer. Now, I emphasize that most of the discussion will be independent of the details of these two Hamiltonians. The only thing that will matter are the symmetries, the degrees of freedom, and the fact that we have periodic or anti-periodic boundary conditions. And in more generally, so H plus will have the one with periodic boundary conditions. H minus is either the same Hamiltonian, but with anti-periodic boundary conditions, or putting a defect for -1 to the F. So that's what I've just said. And we will study 4 fermionic theories, depending on whether L is even or odd, and whether we discuss H minus or H plus. And what we will see, since I assume that there are many people with string theory background here, for even L, we will find in the continuum the Neves-Schwartz, Majorana CFT. And for H plus, we will find the Ramon theory. And for odd L, we will find the Ramon Neves-Schwartz. And for H minus, we're going to find the Neves-Schwartz Ramon. I say right now, to avoid the question, that the case of odd L is notoriously confusing. There's been a lot of discussion of it, about it, whether it makes sense or not. So I will comment about that later. Any questions so far? Okay. So let's discuss the case of even L. So we have symmetries generated by T and -1 to the F. I use the notation which might be confusing. I'm studying 2 systems simultaneously, H plus and H minus, and correspondingly they are translations T plus and T minus. These are not 2 different translations in the same system, but I use notation of the translation operator in the 2 different systems. So for H minus, it's easy to check that these operators satisfy the following algebra. T minus to the L is translation around the whole chain. And since we have anti-periodic boundary conditions, it's not 1, but it is -1 to the F. And furthermore, translation commutes with -1 to the F. So this is the algebra of operators that we study. For H plus, it's a little bit more interesting. First of all, T to the L is 1 because we have periodic boundary conditions. So as we go around the chain, we come back to where we started. This is the meaning of this equation. More interesting, as pointed out by these authors, we have a minus sign here. Translations anti-commutes with -1 to the F. An easy way to see that is that -1, the translation shifts all the operators by all the labels by 1, and -1 to the F is a product of all the fermions in the problem. So it's a product of all chi1, chi2, etc. up to chi8. So if we take the product, and when we shift by 1, or if we do it the other order, one guy has to be dragged all the way from the end to the beginning. So there are L -1 transposition, and since L is even, we get a minus sign. This minus sign can be thought of as being an anomaly between fermion parity and lattice translation. That by itself is already a little bit surprising, because we have this obvious symmetry of lattice translation and -1 to the F. But now we see that the algebra that they satisfy had this minus sign, so the algebra is realized projectively. It also raises another puzzle, that in the continuum, there's no anomaly involving translation. So how are we going to match the Hooft anomaly matching, wherein on the lattice, we have this minus sign, we have this anomaly. But in the continuum, there's no way to get an anomaly between translation and -1 to the F. I'm going to answer this question. In order to see that, let's take this specific example of H plus minus, where we have either plus sign here or minus sign, and just solve the system and see how it works. So since the system is quadratic, we just go to momentum space, we diagonalize the Hamiltonian, and we find this dispersion relation. For H plus, it looks like that. For H minus, it looks very similar, except that for H minus, we have half integer momentum, and therefore there are no zero modes here and here. For H plus, there are zero modes here and here. So if we look at low energies, namely we focus on this part of the spectrum, we see here relativistic dispersion for right movers and for left movers. And similarly here. Here, there is a zero mode, so that's like the Ramon theory. And here there is no zero mode and the momenta are half integers. So this is like the Neves-Schwartz. So the low energy spectrum gives us a complete Majorana fermion, either Ramon or Neves-Schwartz. The modes that come from here, the right movers, and the mode that come from momentum around L/2 are the left movers. So that's what I said here. H plus leads to the Ramon, and H minus leads to Neves-Schwartz. But I emphasize that on the lattice, we have only the lattice symmetry -1 to the F. We don't have separately -1 to the F left and -1 to the F right. These two symmetries appear in the continuum or at low energies only by focusing on low energy modes, minus 1 to the f left has plus 1 here and has plus 1 here and minus 1 here. Minus 1 to the f right has the opposite sign. Now, this actually raises another interesting question. There is no chiral symmetry on the lattice. So how come there is no fermion mass term? How come we ended up with a massless theory, a gapless theory, without doing any fine-tuning? We didn't fine-tune any parameter. We just imposed the symmetries we imposed. And we landed on the ground state. We landed on this system. In fact, in the continuum, we could have added a mass term for the fermion. It does not violate minus 1 to the f. It does violate minus 1 to the f left or minus 1 to the f right separately, but it does not violate fermion number, fermion parity. So how come we did not impose that? We did not impose these symmetries microscopically, and yet the continuum theory or the low energy theory has that symmetry with a relevant operator that violates the symmetry, the mass term. The answer to that is no, but I'm going to phrase it in a slightly different language. Let's start with H plus. On the lattice, there is no minus 1 to the f left. In the IR, it emanates from T plus. So what's the algebra? The algebra is T plus to the L is 1. That's the algebra on the lattice. This is the dispersion relation. And we claim that the way to translate the UV to the IR is the following. The operator T plus of the lattice is given by e to the 2 pi I p plus. P plus here does not mean momentum in the plus direction, but it means momentum in this theory with Hamiltonian H plus divided by L times minus 1 to the f left. So the p's that appear here have eigenvalues which are integers, and we take them to be numbers of order 1, but the important thing is that they are a lot smaller than L. So for modes around here, we would just say that P plus is a number of order 1, and minus 1 to the f left is 1. And for modes around here, instead of saying that P plus is near L over 2, we would say that P plus is again an integer of order 1, and minus 1 to the f left is minus 1. So P plus is the momentum of the continuum IR theory. So the low energy observer says that I see momentum P plus. It's a number integer of order 1, and it corresponds to modes here can have one sign of P plus, modes here have the other sign of P plus. And in addition, we have another quantum number, minus 1 to the f left, which is 1 here and minus 1 here. On the lattice, however, only T plus is meaningful. And the reason is that for modes around here, we can't say whether they have P plus of order plus L over 2 or minus L over 2 with opposite signs of minus 1 to the f left. So in the continuum, this quantity and this quantity are separately meaningful, and they're separately exact symmetries. While on the lattice, only their product is meaningful. I emphasize that even if I'm on the lattice, I'm not taking any limit. L is big, but I'm only looking at low energies and low momenta. There would be no transition from here to here. In the language of condensed matter physics, the only way to tell that the underlying system is on the lattice is to use the Umklapp process, which involves very high momentum. As long as we discuss only low momenta, we cannot tell that we are on the lattice and not in the continuum, because we need to go to momenta which are very large in order to see that. Furthermore, this relation between the UV and the IR operator is exact. Normally, when we write the UV operator in terms of IR operators, there's a power series in 1 over L, and there could be 1 over L, 1 over L square, 1 over L cube, etc. corrections. In that case, this relation is exact, because T plus to the L has to be 1, P is an integer, this is 1, and this is also 1, because L is even. But if I put here any 1 over L square correction, I will mess up this equation. So again, something very surprising. The low energy observer thinks that there are 2 exact symmetries, not just 1. And furthermore, the relation between the UV and the IR operators is exact. It's getting even better. There's an anomaly in the continuum IR theory. This is a nice calculation for anybody who took string theory 101. minus 1 to the f, the total fermion number, and the left-handed fermion number, minus 1 to the f left, anti-commuting the Ramon-Ramon theory rather than commute. It comes from quantizing the zero modes. So there's a minus sign here. We interpret the anomaly that we saw on the lattice between lattice translation and minus 1 to the f. It becomes in the IR an anomaly between minus 1 to the f and the eminent minus 1 to the f left. So we had before two questions. One, how can we match this lattice anomaly involving translation in the continuum where there is no anomaly in continuum translation? And the answer is that lattice translation becomes in the continuum both an internal symmetry and a continuum, and the lattice anomaly is in that internal symmetry. The other question we asked is how come we are automatically at the massless theory without various operators that could have gapped the system? And the answer is that lattice translation becomes induces an internal symmetry. Maybe I should say there's an internal symmetry that emanates from lattice translation, and it does this fine-tuning for us. So here we discuss H+. We could do the same thing with H- with a very similar conclusion. So let's summarize what we found. Minus 1 to the f left symmetry of the continuum is exact. So if we look at, even with large but finite L, we look at low energies, we are not going to see any low energy any operators in the low energy Lagrangian that violate minus 1 to the f left. We are not going to find the mass. There is a mass term, but it's not present in the Lagrangian. And there are lots of higher dimension operators that violate minus 1 to the f left, but they're also not present in the Lagrangian. The point is that this is not an emergent symmetry. It emanates from lattice translation, and it explains this issue I just mentioned, why the fermion is massless without the UV chiral symmetry. If, for example, the fermion mass term is invariant at the minus 1 to the f, but it violates lattice translation, and therefore it violates the eminent minus 1 to the f left. And also we discussed the anomaly, how the anomaly of lattice translation becomes an anomaly in the continuum, or at low energies, an anomaly involving an eminent symmetry minus 1 to the f left, thus avoiding a contradiction. This is what I wanted to say about even L. Let me move to odd L. So here we have an odd number of real fermions. And if we were a mathematician, we would say, we were mathematicians, we would have said, we have a Clifford algebra with an odd number of elements. There is nothing wrong with that, except that there is no minus 1 to the f. For odd number of fermions, we cannot find the minus 1 to the f unless we take a reducible representation. So what are we going to do about that? The most common view in the literature is to declare the problem as inconsistent and simply ignore it. Namely, we say we're not interested in odd L, this is too subtle, we don't want to discuss it. But we can also try and use canonical quantization. And since we don't have minus 1 to the f, we have various options. One is to give up on minus 1 to the f. We say that we take the smallest representation, an irreducible representation of the Clifford algebra. Since we don't have minus 1 to the f, the Hilbert space is not graded, and we just have to live with it. This is the approach I will follow here. Another approach, which is common in the literature, is to add a decoupled fermion that doesn't play any role, except that now the total number of fermions is even, and therefore we can define grading with minus 1 to the f. Alternatively, we simply take a reducible representation of the Clifford algebra, or two copies of the representations of the Clifford algebra, so that we can define the grading. Either way here, tensor products of such systems are confusing, because if we take two copies of these, two copies of with an odd number of fermions, if we do that, then we suddenly we've added two decoupled fermions, so we end up with the wrong answer. And similarly here, if we take tensor products, it's confusing because we don't have the grading that exists in the tensor product. Another approach is to assume that there exists a tensor product and use a path integral to define the system. So what we say there is that we have an odd number of fermions. Let's take the square of the path integral. Now we have an even number of fermions, so we know what we're doing. We calculate what we calculate, and then we take a square root. As we do that, we find the trace of 1 after taking the square root is root 2, and it does not have a Hilbert space interpretation. So either way, an odd number of fermions is subtle, and maybe the right approach is just to declare it inconsistent and ignore it. But I'm going to follow this approach and see where it leads us. So again, I'm studying 2 Hamiltonians with a plus sign and with a minus sign. And I take just an irreducible representation of the Clifford algebra and see what we find. So the UV system doesn't have -1 to the F left, doesn't have -1 to the F right. This is the same as before. In this case, it doesn't even have -1 to the F. So this UV system doesn't have any internal symmetry. The only symmetry in the game is lattice translation. And when we analyze the system in more detail, we see that T to the L, either with a plus sign or with a minus sign, is not 1, but instead it's a funny phase with 1/16. In fact, for the experts in the audience, the 1/16 already tells us that we must be doing something right, because theories of Majorana fermions always have various things with 1/16. When we try to quantize the system, we go to momentum space, and again, we write the dispersion relation. And now the dispersion relation looks like that. We have only one fermion zero mode. It is either at momentum 0 or it's momentum L/2, depending on the sign here. So for all the non-zero mode, it's completely clear what's going on. These are right movers, these are left movers. The right movers have periodic boundary conditions and therefore integer k, and integer momenta, where momentum is measured relative to here. And here we have left movers, which have anti-periodic boundary conditions. And the same thing is here, except the left movers and the right movers are exchanged. So we see just from looking at the spectrum that H plus leads to the Navier-Schwartz-Ramon theory and H minus leads to the Ramon-Navier-Schwartz theory. And the subtlety in the quantization can also be seen in the continuum, because if we study a single Majorana fermion with, say, NSR boundary conditions, there's only one fermion zero mode coming from the Ramon sector, and we have to decide how to quantize it. Do we say that the problem doesn't make any sense, or do we say that there's only one ground state, or do we say that there are two ground states? And these are the approaches I discussed earlier. So let's discuss that in a little bit more detail, and to be concrete, let me study H plus. So in the infrared, at short distances, there are no internal symmetries. At long distances, the story is very similar to what we saw before. We have a new internal symmetry, -1 to the F left, that emanates from T plus. It's not that we have a symmetry T plus and another one T minus. We have the subscript plus here, simply because we studied the problem with the plus sign. The lattice fermions are periodic. And this is the algebra they satisfy. In the UV, we have this algebra with this anomalous phase. And the dictionary between the UV and the IR is as follows. We have a new symmetry, continuum symmetry P plus, whose eigenvalues are integers and positive here, and negative and half integer in this region. And we also have another -1 to the F left, which tells us whether we are in this branch of the spectrum or that branch of the spectrum. And that matches, these two relations match this continuum result that we can get just from studying the continuum theory. So again, P plus, again, I remind the subscript plus is not because it's in the plus direction, but because we study the Hamiltonian H plus, is the momentum of the continuum NSR theory. These are the right movers and the left movers. And again, on the lattice, only T plus is well defined, while in the continuum, we have two symmetries that are separately meaningful, and the details are as before. And finally, as in the previous example, this relation between the UV operator and the IR operators, this relation is exact without finite L corrections. Now, we can also study H minus, and it will be essentially the same, except that some signs are flipped. So this is my discussion of the Majorana chain. Are there any questions at this point before I change the topic? Okay, I lost everybody. We'd like to go now from the Majorana chain to the Ising model. For string theorists, it's kind of straightforward. What we need to do is to perform the GSO projection, namely sum over the spin structures, except that we would like to do it on the lattice. There's huge literature on the subject, but I'll phrase it in a way that resonates with the way high energy physicists think about it. So we're going to sum over the spin structure, and we'll do that by first doubling the Hilbert space. So we take the same Hilbert space we had before. We take 2 copies of it, not a tensor product, but 2 copies. It's a direct sum. And we'll denote anything in the bigger Hilbert space with a tilde. And we'll take the Hamiltonian to be H minus in the upper left block and H plus in the lower block, right block. So this would be the Navier-Schwarz theory. This would be the Ramon, but we're doing it on the lattice. So this is whether we do or do not have the -1 to the F defect. And we have a translation symmetry operator because we can translate in this block using the lattice translation we discussed before. We can translate in this block with a lattice translation we discussed before. Furthermore, we have a new Z2 symmetry. Since we double the Hilbert space, we have what is sometimes called the quantum Z2 symmetry, which is 1 in the 1-1 block and -1 in the 2-2 block. Now, let's analyze this system in more detail. And again, we're going to start with the case of L even, and then I'll discuss L odd. So we have a doubled Hilbert space, H tilde, but some operators are non-local relative to each other. So we imitate what we do in the continuum, and we are going to project. We have the Z2 symmetry, eta tilde, this is quantum Z2 symmetry, and we have -1 to the F. So we can project on states such that this product is 1, and that leads to the Ising model. So if we take the Hilbert space that we had before and we perform this projection, we find the Hamiltonian of the Ising model. And you can use a Jordan-Wigner transformation and write it in terms of X and Z Pauli matrices at the sites. Note that the number of sites of the Ising problem is half the number of sites in the fermionic problem. So this is an exact change of variables here. Alternatively, we can project on this object being -1, and this leads to a Z2 twisted Ising model. The Ising model has a Z2 symmetry, and therefore we can consider a twisted one where we flipped one of the signs here. So this is the Ising model with a Z2 defect, or the Ising model with anti-periodic boundary conditions. Now let's discuss the symmetries of these 2 problems, either the Ising model or the twisted Ising model in more detail, and express them in terms of the fermionic problem we discussed earlier. Because of the anomaly, T plus does not commute with -1 to the F. This is a point I emphasized earlier. Lattice translation with periodic boundary conditions does not commute with -1 to the F. With anti-periodic boundary conditions, it does commute with -1 to the F. And since, because of that fact, T plus does not commute with the projection we perform. We perform the projection on -1 to the F, and therefore T plus is not a good symmetry. Related to that, this translation symmetry of the double fermionic problem does not commute with the projection, and therefore it does not act in the projected Hilbert space. Therefore, this T tilde, the translation of the fermions, is not a symmetry of the problem. What can we do about that? Well, we can take the square of that. So whatever minus sign regarding the anomaly goes away. So the square of that does commute with the projection. Eta tilde, the Z2 symmetry, also commutes with the projection. And therefore, they both act in the projected Hilbert space. So we end up with 2 symmetries, T Ising, which is the fermionic translation square projected to the Ising subspace, and eta, which is a Z2 symmetry, which is the symmetry in the big Hilbert space projected to this smaller Hilbert space. And they satisfy this algebra. Since we took translation was the fermionic translation square, we can raise the Ising translation only to the nth power to find 1. And this is the Z2 of Ising. So far, it is extremely conventional. And in fact, everything I've said so far here is in one form or another in the literature. Now we'll say something that also exists in the literature, but from a totally different perspective. Let's consider this operator in the fermionic theory, where we put 0 in the 2-2 block, in the 2-2 entry here, 2-2 block of the translation. So we perform translation, but only for the Navier-Schwarz part of the story, not in the Ramon. Instead, in the Ramon part, we put 0. This operator commutes with the projection because the sign, the problematic sign I discussed earlier, is only in this block. So this operator commutes with the projection, and it clearly commutes with the Hamiltonian because it commuted with the Hamiltonian even before the projection. The only funny thing about this transformation is that it has a zero here. Namely, this is not a unitary transformation. So we see that we have a new symmetry of the lattice Ising model. It's actually related to Kramer-Venia duality in a way that I'm not going to explain here. If I have time, I'll discuss it later. So what we're going to do is take this operator that commutes with the Hamiltonian, commutes with the projection, project it to the smaller Hilbert space and denote it by D. Mathematically, this is known as a partial isometry. A partial isometry is a unitary transformation on the orthogonal complement of its kernel. So this operator has a kernel that comes from the zero here, and it is a good unitary symmetry, a good unitary operator on the complement of the kernel, but it's not invertible because it has a kernel. We can square this transformation. So we said already that while T with T plus here is not a symmetry, its square is a symmetry, and that's Ising translation. So when we square this guy, we find Ising translation times a projection operator. Finally, we can express D in terms of the operators X, Y, and Z, and check all these statements explicitly. So the way I motivated it here was starting with the fermions, and then I had a construction with fermions, and then I did the bosonization or the sum of the spin structures and derived the Ising model, and derived this operator. I could have short-circuited this whole thing and pull out of a hat an expression for D in terms of X, Y, and Z, and check explicitly that it commutes with the Hamiltonian, that it's not invertible, and it satisfies this algebra. All these things can be done very explicitly on the lattice. So what happens to this symmetry in the continuum? In the continuum, it flows to a known non-invertible symmetry of the continuum theory, which I denote by this curly D. And I use, if you notice my color coding, this purple is always the UV, this red is always the IR, and this thing is reserved for emanant symmetries. So the story is very similar to the emanant symmetries we discussed before. The UV lattice translation is the product of, so that's a UV operator. The IR person says we have something coming from ordinary continuum translation with integer P, where here in the denominator we have 2n, which is the total number of sites, times another operator, which is this continuum operator, curly D. And the 1 over root 2 here is because of the normalizations we picked. This continuum operator satisfies the following algebra. This is trivial. This is just a statement that it's a Z2 symmetry. This is the statement that we have periodic boundary conditions. And D square is 1 plus eta. The reason is that as we, in the continuum, we take n to infinity, so this thing drops out. And this eta commutes with D. So this algebra had been written before by these people and many others. But I emphasize that it's not the same algebra as the algebra we got on the lattice. The algebra on the lattice of this symmetry D involves also lattice translation. So what we see is that on the lattice, this non-invertible symmetry D mixes with translation. In the continuum, this operator goes to 1 in the continuum, and therefore we get a different algebra. So we really have two different algebras here, one on the lattice and another one in the continuum. So this D is a non-invertible symmetry. It emanates, this curly D in green is a non-invertible symmetry. It emanates from the lattice D. And again, it is exact in the infrared theory. We could write operators in the infrared that violate this symmetry, this curly D, in the continuum. There could be such relevant operators, even such irrelevant operators. It's easy to write them down in the Ising model, but they are not present if we start from the Ising model that we started with. So the Ising CFT can be deformed by various operators, either relevant or irrelevant, that violate this symmetry. For example, so they violate that symmetry. But these operators are not present, even though there is no operator, there is no symmetry on the lattice that satisfies this algebra. So on the lattice, again, we have only T Ising and D. The continuum, we have P and D, but they satisfy different algebra. And again, the relation between the continuum, or the low end, the infrared, and the ultraviolet is exact. There are no finite n corrections. So this is what happens when L is even, what happens when L is odd. In this case, there's no -1 to the F. There's no such internal symmetry, and therefore no projection is needed. So we are just going to follow our nose and see what we find. We still perform we double the Hilbert space to find H tilde. There's no need to perform the projection. We can use the Jordan-Wigner transformation and find this Hamiltonian. Notice that it involves also the Y sigma matrix. So this is the Hamiltonian, which had been written earlier by these people, and it flows in the infrared to the continuum Ising CFT with a non-invertible defect, which had been studied by these authors. So what we see here is that, first of all, the fact that we landed on our feet here, and we found a system that is interesting and had been studied earlier, gives more credibility to our treatment of the odd L fermionic problem. But we also tied together the fermionic problem and the Ising model and the twisted Ising model. We tied them all together, and we did the bosonization on the lattice, and everything is done at finite n. We match the symmetries, including in non-invertible symmetry, and we also match the anomalies. I would like to change now the topic, so before I do that, are there any questions?
Nati.
Thank you, Shiraz. I hope that somebody would rescue me and ask a question. I know who'd come to me.
Okay, I have two sort of related questions. The first one is that is it correct that translations by odd steps on the lattice become in the continuum some global symmetry, while translations by even steps on the lattice sort of become translations in the continuum?
Are you talking about even L or odd L?
I was talking about even L to start with.
Okay. This is almost correct. It's almost correct because if the translation is by a finite power, then whatever finite power you have, it is always either one or the internal symmetry. Because you take L to infinity, and you take, say, 5 translation by 5 sides, 6 sides, etc. The continuum translation part of it is 1. Your statement is correct. We can ask another question: what if the number of steps I take in the power of t grows with L? So it is L over 1,000, for instance. So I make more and more steps. Then, if it is even, then it is just continuum translation. If it is an odd, it's a product of continuum translation and internal symmetry. So it's you really have to specify whether you mean by translation by a fixed amount as you take L to infinity, or the number of steps grows with L. In either way, there are 2 answers depending on whether L is even or odd.
Okay. So the second question along these lines is that then it seems that your point of view is that if you were an IR observer and you detected this exact symmetry with there being no reason for it to be exact, it's sort of like giving you a clue as to the underlying UV structure of the theory, right? The lattice on which the UV stuff lives.
Well, you don't even know that you have a lattice.
Right.
For all you know, you're in the continuum, and that symmetry is exact in the UV. So if you're an IR person, so let's go back to the fermions. And you're an IR person, and you find that there is -1 to the F and -1 to the F left. You can easily say, well, it came from some UV system at high energies that has these 2 symmetries. Okay. And I could very well find some 4 Fermi interactions that preserves these 2 symmetries, and it could be in the Hamiltonian. For example, TT bar deformation that people like to study fits the bill. But there are also many others. Now, so there could be irrelevant operators, and this system could arise from some higher energy theory, even in the continuum, that has these two as exact symmetries.
Okay. Yeah.
But what we see here is right. So if you are a low energy person, you really need processes with momentum of order L to tell that you have a lattice. Otherwise, you can't tell that, because it's not that there's some, you just have to measure another higher dimension operator. So you have to measure some course. Normally, when the symmetry is violated, you just have to go and find an irrelevant operator that violates it. That's not the case here. There's no irrelevant operator that violates it. So it's not the standard rule about approximate.
Yeah. Thanks a lot. Yes.
Okay. All that I said so far, including answering Shiraz's question, smells like this thing is a very latticey thing. This phenomenon relies on having a lattice at short distances. Otherwise, it cannot happen. And I assume that most of you are continuum people, so you say, who cares about the lattice? I'm only interested in the continuum. So let me give you a continuum example where the same phenomenon happens. And that is the explicit breaking of winding symmetry. So I'm going to consider the C equals 1 compact boson and use the dual variables, phi tilde. I do not know whether there are condensed matter people in the audience or not, so let me just give the dictionary. Instead of C equals 1 compact boson, they refer to it as the Luttinger liquid. And then phi tilde, the dual boson, is usually denoted by theta. So we studied this system. It does not have the winding symmetry because of the cosine phi tilde. And this is winding symmetry because we use the dual variables. So we have only the U1, the momentum symmetries. I'm using the string theory terminology. In condensed matter physics, this U1 is called charge, and the winding symmetry is called vorticity. So we have only the momentum symmetries, but no winding symmetry. So let us first set lambda to 0. And we have a one-parameter family of conformal field theories labeled by R in this system. And that's actually the UV now, because I don't have a lattice. And there's some special points. It is R equals 2. This is the big AT point. And R equals 1. We have SU2 level 1, WZW1. I assume that everybody here knows a lot about this picture, so I don't have to discuss it in detail. Now we turn on this perturbation and ask what happens. If R is bigger than 2, this operator is irrelevant, and therefore this gapless spectrum remains gapless, and we find an emergent U1 winding symmetry. In contrast, when R is less than 2, this operator is relevant, and therefore it gaps the system. So with non-zero lambda, we have a gapped system here and a gapless system here. And if we are here at large R, this U1 winding symmetry is violated by irrelevant operator. It's not an emanant symmetry, it's an emergent symmetry. This is the standard story. So everything on this slide is something that you studied when you studied field theory in 2 dimensions. This is completely standard and it's ancient. Let's add a chemical potential to the only symmetry in the problem, the U1 momentum symmetry. This is related to work of Haldane from 1980, although I phrase it in a slightly different way. So we have the momentum charge. The momentum charge is given in terms of the original scalar is phi dot with some coefficient. This is the charge. And in terms of the dual scalar phi tilde, it is that. So the charge I'm talking about is the winding charge of the dual scalar. So this is the winding charge of the dual scalar. And now we want to turn on a chemical potential for it. So we take the same Lagrangian we had before, and we add this term. So the cross term here is the coefficient times this charge, hence it's a chemical potential. And there's an additive constant that doesn't make any difference. So we live on a circle. X is identified with X plus this boldface L. And we arrange the chemical potential such that the corresponding charge is near an integer little q. Okay, so we'd like to solve this system. The way to do that is, first of all, to change variables. Instead of discussing phi tilde, we can go to phi hat, which is phi tilde plus this 1 plus 2 pi q x over L. Notice that since q is an integer, this change of variable is okay, because if I shift x by L, shifts phi tilde by 2 pi times an integer, which is consistent with the periodicity. So we end up with this Lagrangian, with this action. This we just copied. Here we did the change of variables. And here, all the dependence on the chemical potential appears here. So for lambda equals 0, this is the same as the problem we had before. This is kind of a sanity check. If we have both momentum and winding symmetries, and we turn on chemical potential for the momentum symmetry, then we haven't done anything, and that's known as spectral flow. So this is kind of a sanity check that we did not mess it up. And now we would like to see what's the effect of breaking the winding symmetry. So we take the original system that has no winding symmetry, we introduce the chemical potential, we change variables, we tentatively turn this off, we found an answer we know, and now we turn lambda back on to be non-zero. So for non-zero lambda, this winding operator can be relevant or irrelevant. It's cosine phi hat. Would be relevant or irrelevant, as we discussed earlier. However, it depends now on x. And if I make Q large, this x dependence tells us that this operator oscillates rapidly in space. In terms of space momentum, as opposed to target space momentum, this operator oscillates very rapidly. And since it oscillates very rapidly, its correlation functions vanish. In other words, if I consider correlation functions of operators with low spatial momentum and low energy, then I can compute order by order in perturbation theory in this lambda, and I always get 0. So this operator doesn't act in the low energy theory. This is actually quite surprising, because what happens now is that the winding symmetry is an emanant symmetry. It emanates from UV translation symmetry. See, this problem has two different notions of translation. The UV person says that translation shifts x and does not touch the field phi tilde. In terms of the phi hat variables, translation shifts x and shifts phi hat by a constant, such that this is invariant, this is invariant, this is invariant. So the UV person says translation shifts x and shifts phi hat by a constant. The IR person says I shouldn't shift phi hat. For me, translation shifts x and does not shift phi hat. And this operator violates that symmetry. So let's examine various operators. An operator like cosine phi hat looks very natural from the IR point of view, but it's not invariant under the notion of translation in the UV. And therefore, this operator is clearly not present. So we cannot get here corrections proportional to cosine phi hat, because this violates a UV symmetry. More interesting are operators like that. This operator does exist in the spectrum and does exist in the action. This operator is invariant under UV translation, but it's not invariant under IR translation. So the low energy observer, IR translation is not an exact symmetry of the problem. But the low energy observer who tries to see whether the IR translation is a symmetry or not, will have to perform scattering of objects which carry very large momentum in the IR, momentum of order little q. And therefore, if we only limit ourselves to low energy states with low momentum and low energy, we would say that we have this new symmetry, winding symmetry. It's an emanant symmetry, and therefore it is as if this operator is not there at all. It's not that this operator is not there because it is irrelevant. It is not there, period, because it does not have any correlation functions. So the emanant symmetry is not violated by relevant or irrelevant operators in the low energy theory. It's an exact symmetry, not an emergent and accidental symmetry. Before I change topic, are there any questions about that thing, how we got it in the continuum? Well, everybody accepts. This is a rather surprising result, I gotta say, that you get an exact symmetry from nowhere and you get it for free. Okay, so I'm going to move to the third topic and I'll be here very brief. I'll give another example of the same phenomenon, and that's the lattice Heisenberg chain, known as the XXZ model. So we have Pauli matrices at the sites, We have periodic boundary conditions, so J is the same as J plus N. And we're writing Hamiltonian, which has X, nearest neighbor X, nearest neighbor Y, and nearest neighbor Z. This model is, by the way, exactly intervalable, but I'm going to make statements which are true even if I deform it such that it's no longer intervalable. The internal symmetry in the UV is O2, because I can rotate X into Y, and I can also flip the sign of X and Y. And that's a subgroup of SO3, which exists only with symmetries SO3 when lambda Z is 1, and then we can permute all these matrices. Now, this model is solvable, but what's more to the point here is that depending on lambda Z, it flows to the free compact boson with a radius larger or equal 1. So for lambda Z equals 1, it flows to the compact boson with R equals 1 in my convections. So for lambda Z equals 1, we have the Heisenberg chain with SO3 symmetry corresponding to R equals 1. Now, what about the winding operator cosine phi tilde? So imagine we try to write the low energy theory. It preserves GUV. It preserves the O2 symmetry. And depending on lambda Z, and therefore depending on the radius R, it might or might not be irrelevant. Specifically for R equals 1, which corresponds to lambda Z equals 1, this operator is relevant, and it preserves the GUV internal symmetry. So we could ask, why isn't there at lambda equals 1 an SO3 preserving relevant operator? In terms of the WZW model at lambda equals 1, there is an operator invariant under the diagonal SO3 whose dimensions are a quarter. So this operator is very relevant. It's invariant under the UV internal symmetry. And yet we say it's not there in this, it is there in the spectrum, but it's not there in the low energy effective Lagrangian, and therefore it does not gap the system. In other words, why are these models robust? Why are they stable? So the answer is that the model flows to this one with a factor of 2 here. And there is an eminent, non-emergent Z2 symmetry, which started its life as lattice translation. So if we look at the original model, and we look at what's the low energy effective action, it's this one. And this operator is irrelevant for R bigger than 1, and it is relevant for R less than 1 that corresponds to other values of lambda. Not only that, we have no terms with cosine n phi tilde with odd n, so there cannot be even cosine 5 phi tilde in the low energy theory, which would be irrelevant, but it's not there anyway because of the eminent Z2 symmetry. This eminent Z2 symmetry again arises from lattice translation. This is the continuum momentum, and this is the generator of that Z2 eminent symmetries. Part of my color coding, anything eminent has this green. So it's the same notation as before. T is lattice translation in the UV. P is the momentum of the continuum theory. This C that appears here generates an internal symmetry. In terms of continuum language, it's e to the I pi Q momentum plus Q winding. So that's a symmetry of the continuum theory. Normally, we would say, oh, it's an emergent symmetry because it's not there microscopically. But in fact, this symmetry is exact. It's exact because it emanates from lattice translation. So again, the same words as before. On the lattice, only the left-hand side is well-defined because there are states in the spectrum which have P of order n, and we can't tell whether P comes from 0 or from n over 2. And we can't tell the value of C. But as long as the eigenvalues of P are smaller than n, much smaller than n, there's a clear separation between this factor and that factor. And therefore, the low energy observer has well-defined C and well-defined momentum. And again, as before, this relation between the UV and the IR is exact because putting here higher order corrections in 1 over n, which is typically the case when we relate UV to IR quantities, such relations cannot be present because they would mess up the equation that T to the n, T to the number of sides should be 1. Now let me summarize what we saw. We discussed microscopic translations for example, lattice translation, but I also gave an example in the continuum. And they can lead to an eminent eminent internal symmetry. Unlike standard emergent or accidental symmetries, this symmetry is exact at low energies. It's not violated by relevant or irrelevant operators. So there can be relevant operators that violate the symmetry, but they are not present in the action, even though there is no corresponding symmetry at short distances. And we discussed several examples of that. First, we discussed 4 versions of the Majorana chain, depending on whether the number of sites is even or odd, and depending on whether the boundary conditions are periodic or anti-periodic. And they flow to the 4 different Majorana theories in the continuum, Never-Schwartz, Ramon, and NSR and RNS. In each case, we had microscopically some -1 to the F only when L is even. We didn't have it when L was odd. And -1 to the F left or -1 to the F right did not exist microscopically, but they emanate from lattice translation. And furthermore, the microscopic anomaly between lattice translation and the internal -1 to the F is matched at low energies by an anomaly involving internal symmetries, thus avoiding the question of how come there could be an anomaly in translation. There's an anomaly in translation in the UV, but in the continuum, there's no anomaly in continuum translation, but instead, lattice translation gives us an internal symmetry, and that internal symmetry can have an anomaly. Then we summed over the spin structures, and the 4 Majorana theories, the 4 fermionic theories, lead to 3 bosonic theories, which do not depend on the spin structure. These were Ising, twisted Ising, and Ising with a duality defect D. D is because of duality for reasons I did not explain here. And these models, these lattice models, so this is an exact statement on the lattice, and these models flow at long distances to 3 continuum Ising models with various defects, no defect, the twisted Ising model with a Z2 defect, or with a non-invertible duality D of the CFT, with the duality defect in the infrared. And furthermore, we saw the non-invertible symmetry D of the CFT arises or emanates from the lattice symmetry D. And as I emphasized, the lattice D and the continuum D satisfy different algebras. We also discussed an example in the continuum, the system with a U1 global symmetry with a chemical potential. It can have an eminent symmetry, which is kind of surprising because there's really nothing there that tells us that would happen. The only thing that happened was that we turn on some chemical potential for the global U1 symmetry, and we found the eminent winding symmetry. I did not discuss it here, but in this case, we can actually prove on general ground without even saying what the action is, that there's a certain anomaly in the problem that forces us to have something peculiar like this at long distances. This is without even telling you what the system is. We also discussed some various spin systems, like the Heisenberg chain, and they lead to a Z2 eminent symmetry, which again starts its life as lattice translation, becomes in the continuum an emergent symmetry, an eminent symmetry, an eminent internal symmetry, and there are various anomalies associated with it. So the anomalies involving lattice translations are matched in the infrared by anomalies in internal eminent symmetries. And we exhibited that in some examples. I did not discuss others. In the papers, we discuss others. First, we discussed the Majorana chain, and we saw how such an anomaly in the UV is matched with internal symmetries in the IR. The example I mentioned with the chemical potential can be phrased also as an anomaly, and the anomaly corresponds to Luttinger theorem and filling constraints in condensed matter physics. And the example with the Heisenberg chain, again, there's an anomaly. I did not have time to discuss it, which corresponds to the Lipschutz-Mattis type theorems of systems like that. So I'm over time, so I'll stop here. Thank you.
I have one question.
Yep.
Okay, so in the IR, does the relevant operator also include those operators that are, for example, irrelevant in the UV, but that becomes relevant in the IR, like these dangerously relevant operators.
Right. An excellent question. So the operators that could mess up the story in the infrared are operators that violate the emanant symmetry. So you could ask, the way I understand your question is, what is the corresponding operator in the UV? And the operator in the UV that would mess up this story is an operator that messes up lattice translation. So if we impose lattice translation in the UV, by imposing lattice translation, we kill these bad operators. If we change the lattice system by preserving only translation by two sides and violating translation by one side, the system will no longer be gapless. We are not going to find this emanant symmetry, because the symmetry really started its life as translation. The funny thing about it is that it satisfies a different algebra. Translation of the lattice satisfies T to the L is 1. In the continuum, out of that, we got two symmetries. One of them is a space symmetry, ordinary translation, and the other is Z2. But the Z2 symmetry is more sacred than an ordinary emergent symmetry.
I see. Okay, thank you.
I have a question, Nati.
Yeah, Sveta, good to see you.
Are there examples involving, let's say, abelian or non-abelian gauge fields on a lattice with this type of phenomena?
Yeah, excellent question. In a way, in low dimensions, the answer is obviously yes. But what you mean by the gauge fields is not so clear. For example, the Heisenberg model that I presented can also be described as a CP1 model, which has gauge fields.
Yes.
In higher dimensions, it gets a little bit trickier, and this is something I'm currently working on.
Okay, thank you.
So I'm giving you an unsatisfactory answer, in the sense that the answer is yes, and I understand it, but in those cases where the gauge symmetry is kind of a fake, like in the CP1 model. But in the corresponding systems in higher dimensions, where the gauge fields are something which is much more meaningful, like there's a photon, then
Yes.
the situation is more subtle.
Thank you.
Rajesh, you had a question?
My question was the same as Asrat's, actually. So you answered that, the one about the relevant operators and what they would correspond to in the UV. So, yeah.
So, hello, I had a question.
Yeah. Oh, hi.
Yeah.
Good to
So you started with the statement that there is a homomorphism between this GUV and GIR.
Yeah.
So now, so that statement has to be modified, if I understood that right. That
Not
because
quite.
of them.
So you're referring to this one? Not quite, because I was careful here.
Yeah. So how do I understand this emanant symmetries?
Okay. So if I discuss only internal symmetries, so here I discuss only. I was very careful with the language. If you discuss only internal symmetries, then the symmetry is not here, but in the path of GIR, which is not in the image of GUV. From that point of view, it looks shocking that there's something new. There's another way of doing it, where I defined here also the bigger symmetry group on the previous slide, this curly G, which is the full symmetry group that involves also translation. So we can repeat this analysis with the full symmetry group, including translation. And then the group theory is a little bit more interesting. And then there is a homomorphism from the curly G in the UV to a curly G in the IR. But the situation is a little bit more interesting. And in this case, we also take some L to infinity. So the proper way to do that is to keep L fixed we have a proper symmetry group in the UV, a proper symmetry group in the IR, which is the symmetry seen by limiting ourselves to low momentum and low energies. And then we have a similar story about the homomorphism. So then there it's really interesting how this, there we can really see the symmetry is acting in a non-trivial way if we use also the full symmetry group script G, which involves also the translation in the UV. So the answer to your question is that here I was very careful to write it in a way that will end up being correct, because I limited myself only to the internal symmetries. And this is the homomorphism, and this symmetry, the eminent symmetry, is not here, and it is here, and it looks very surprising that it is exact. The more complete story involves the full symmetry group. As you said, it's not a modification of this statement. This statement is still correct, but there it takes more time to explain how the symmetries mix together. But the story is, there's always a homomorphism, right? It's the reason there's a homomorphism is what I wrote here. Any symmetry operator in the UV is a symmetry operator in the IR. It might be trivial, it might be nuanced, but whatever is a symmetry remains a symmetry. Did that answer your question?
Yeah, I was trying to ask whether there is a group theoretical characterization of the eminent symmetry. Should I think of it as some kind of a quotient of UV by IR or something?
Yeah, okay. The quick answer is no. The quick answer is no, but you see what the eminent symmetry tries to be? It tries to be a quotient of GUV, the full GUV. So if I'm talking about this GUV, ordinary internal symmetry, it's not there at all. If, however, I'm interested, I'm discussing this curly G, the full GUV symmetry, the eminent symmetry tries to be a quotient of it. A quotient, so we discuss translations, for instance. I take T and impose T squared equals 1. So in that sense, it's a quotient. But the quotient is not a symmetry. It doesn't commute. Performing the quotient is not a symmetry, because T squared is a non-trivial operator in the theory. We cannot set it to 1. In fact, it's one of the symmetry groups. So the group theory is a little bit more involved.
Could you tell me in the quotient, what is the denominator? So you take the curly GUV and then...
The curly GUV, and you quotient by a certain subgroup of it. But so let's imagine we have ZL translation. So imagine L is even, and you say, let's quotient it by the element T squared. So we quotient by ZL over 2, and the quotient is Z2. Wonderful, but this Z2 is not a symmetry, because if G is a symmetry, the quotient of G is not a symmetry. So the group theory is more important.
So can I say that the eminent symmetry is that there's a quotient of the curly GUV, which then becomes part of GIR, curly GIR or something? Is that?
No, it becomes part of the non-curly GIR. The non-curly
Oh, it becomes part of because it's not translation anymore in GIR.
Yeah, it's no translation, just pure internal.
So
there is
that.
So group theoretically, you're right. This is what's happening here. But this completely obscures the physics, because the quotient is not a symmetry.
Right. Okay.
So
just one more question, if I may. So if I know the UV symmetries and IR symmetries, say somebody gave me a model, there's a UV model and there's an IR limit of that, and if I know all the symmetries, can I say that which among the IR symmetries are eminent? Like, how do I? Is there a systematic algorithm to kind of check everything
you need also to know how every symmetry operator in the UV is mapped to a symmetry operator in the IR. If the same person who gave you the model and the symmetries in the UV and the symmetries in the IR also told you how they map, how every symmetry operator in the UV, what it corresponds to in the IR, then yes, the answer is yes, you can find which part is eminent and which is not.
And this map
But
you need to know
just-
exactly,
just
not in
start
some
with-
one bell.
Sorry?
Is that right? This map you should know exactly, not in some one bell expansion or something.
Oh, that's right. That's right. It should be an exact map. Because, so for internal symmetries, it's this system, this fact. So first, just say forget any transformation that acts on the coordinates. So this is this map from the UV to the IR. So that's a standard homomorphism. So these are the standard symmetries in the UV and the IR. Everything is wonderful and completely standard. But by doing that, you miss a crucial element, that there could be elements in this GIR which are actually exact, even though this reasoning would tell you that they are approximate. And that part comes from examining also the curly G, which is the full symmetry group. So that person who gives you the model in the UV and the IR, if that person also gives you how every symmetry transformation in the UV is mapped to symmetry transformation in the IR, then you can tell what happens. And this is very much like these equations that I had a billion times here in the various models, like, for example, this equation. This equation tells you how a UV symmetry is a product of two IR symmetries. So the IR symmetry is bigger. It has continuum translation in internal Z2, and the group element T in the UV is mapped to this product. It's kind of surprising that in this talk, I did not present a single new physics result. I just repackaged things that are known in a different language. So I want to make it clear, I did not present any new physics result here. I'm not claiming any credit for any new physics result, except the repackaging.
So Nati, in the continuum example that you had, or others like that, I was trying to understand a bit better. So is it the case that you that this sort of intertwining of the internal symmetry with the space-time symmetry, this in this particular example that you showed, it evades the Coleman-Mandula-like theorem because of this explicit breaking of because there was this explicit X dependence in the transformation in the operator, and is it because of something like that? I mean, because if you had a Coleman-Mandula-like situation for a Lorentz invariant theory, would you be able to still have this kind of?
You're really asking me two questions. One is, can I have examples with Lorentz invariants? The answer to that is that I do not know, and maybe you can prove along the lines you outlined that this cannot happen. It can happen either when there's a lattice, or in this case, we have the chemical potential, so it's still continuum, but we don't have Lorentz invariants. Maybe that's the case. More generally, how this thing, if there's an interesting interplay between this and Coleman-Mandula, not only don't I know the answer, I'm embarrassed to say that after giving a billion talks about the subject, nobody asked me that question, and I didn't think about this question. So every other question I've already been asked a billion times, but this is the first time I hear about it. This is a compliment to you, Rajesh, that I have not heard this question. I didn't think about it, and I don't know the answer. I think it's a fascinating question. There are other fascinating questions I thought about, and I don't know the answer. This is much more interesting because I didn't even think about it.
But thanks for a beautiful talk.
Thank you. And I apologize that I cannot answer this question.
Are there other questions before we end the talk? Okay, let's just thank the speaker. Thank you. Yeah, we end the talk here.
Thanks. Thanks a lot. See you.
Thanks for a great talk, Nat.
Thank you.